Hi, can you hear me?
Hello, I can hear you, Jack.
Okay, sounds good. Thanks for joining.
Great.
So feel free to ask all the questions you want of Tushar and the modeling space and things like that. So we got him for the hour today.
Amazing, amazing. Well, it's great to meet you. I know you've been chatting with Yasha.
Yeah,
Just
trying
jump
to.
into Yeah, yeah, yeah.
It's hard to keep up with you guys.
I'm not sure if that's a good or bad thing.
Yeah, I talked to him about coming to visit you guys sometime too. So
Yeah, absolutely. That'd be brilliant. I know Yasha told me that he's away for a little while. Um,
Mhm.
travel.
So for me, it probably wouldn't be for a while anyway. So
Yeah, yeah.
Hi, Jack.
hi, how you doing?
Oh,
I see you posting. Hi, Matt. Hi, Elf.
I first time to see you, Jack.
So,
Your voice gave me
yes.
indication you are very young man.
No,
You
no,
are
I'm a grandfather of three. My
really,
grandkids are my grandkids are one, soon to be two, 6 and 8. Yeah.
really,
Oh yeah. I mean, I tell everybody, as we as we go through things, my kids are 28, 34, and 36.
really.
Oh yeah. Yeah. Uh,
Your voice is very young, man.
yeah. Uh,
You caught me by surprise, buddy.
yeah. Uh,
So anyway, Jack, I think I looked at your paper that you are submitting for the
uh,
what
I
future
so
future
so
technology initiative.
I said I could submit. The question is that I wasn't sure if somebody wanted to also edit it and things like that. I mean, if nobody wants to edit, jump in, do whatever they're going to do, then I may not
I
submit it.
I
So we
I
we have to
I,
decide
I
by Monday.
Yeah, I looked at it. Maybe you can add references to all these webinars I had with companies like IBM, and just to show people that there is activity happening. No, it's not just we are talking.
Yep. Yeah.
I
No.
also
I
send I also send Jack today
I
um,
I
an
read it. I
article.
saw.
Yeah, good,
Yeah.
good, good, good. Two articles which are also important. You can cite those, but besides the citations, I think I'm not familiar really with the process in OCB. What you wrote is good enough to at least start a new track under this what future technology initiative.
Um. Okay. So we can take it offline for sure.
Yeah,
Okay.
I think it's enough for now. Yeah.
Oh. Okay. Um, Let me look. I thought I saw there's Tushar. Thanks for joining. We're going to give it 1 minute, Tushar, and then we're going to kind of jump in. I know people have been anxious to connect with you, talk to you. We have a number of different, as I sent you, we have a number of questions, things like that. And just as the group's joining, in the share folder, we have kind of the place where we're pulling together proposals, the abstracts for submission for the breakout. I did post a neuromorphic two-pager that Heshen was just referring to. But also, one of the things that we're going to do as a group is as part of the modeling work. Um, Winston and his team, and King Shuck's here as well. The team from Keysight has pulled together essentially infra.proto, or kind of the initial version of a schema. And so I reached out to OCP about standardizing a schema which allows us to look at it from a system point of view. And they were very supportive. And so we're going to start working. I think it'll be a little bit less than a month, but we're going to propose a system level schema for us to do system of systems. And essentially, if you look at our hardware software co-design, how do you start to, the materialization of kind of the polymorphic as system of systems, which allows us to do compute, communication, data, in terms of connecting those elements around services. Yasha and Dan are on the call today. They've been doing work around algorithms, mapping algorithms, and we have a conversation around which fits into the polymorphic space about mapping task tags into resource graphs. So Yasha and I have been having that conversation as well, and we're going to continue down that path, which allows us to fit into the schema, which connects to what Tushar has been driving around modeling. And so I have the action from Tushar that I'll do data services and storage for AstroSim regardless of how we actually move forward. But so we're going to start to pull all of that together. But not only do we have kind of the path that we're taking on modeling, the path that we're actually moving forward to OCP Global Summit, but in talking about schema, the OCP global community was very, very happy and excited for us to propose a standard way for us to do schema around this modeling framework. And so we're going to do our proposal July 9th into the overall AI open systems for AI, which is really the AI governing body. So we'll keep sharing status, doing things like that. We'll use the share drive so everybody gets to see the work going on. You can participate however you'd like in terms of this, but we're on kind of a short timeline to make sure that we can connect our dots for the global summit, and that's the space we're going to go. So that's kind of the administrivia, giving people exactly 5 minutes to kind of join the call, and I will shut up so that Tushar can do his intro and we
check one quick question on the submission part for the AI fabric. Are we doing the common submission, or each person has to do its own submission for the AI fabric part?
So for the AI fabric part, Jay was going to work on scale up. And so if there's something around scale out that you'd like to do, connect with me afterwards, but you'll see the document in terms of that, Prakash. So so he's going to do scale up. And if you'd like to actually work on a piece around scale out as we start to work that. So if you look in the I think it's global summit in the proposals directory, you'll see a proposal document which has the part Semantic is working on. Jay will add Yasha's parts there, my parts there, Kinshuk's parts there, Tushar's parts there. So
so I can add my part there too.
Yes, and then on Monday we're each going to submit into the OCP server breakout session. We're going to submit abstracts, and then whatever we decide to submit on Monday, I'm going to collect all that as a group, create a theme. I'm going to speak to John Stewie, who runs our OCP server, and just say, here's everything we have. Here's how they're all connected. Here's our theme. Here's how we're working together. Here's how we're going to drive our standards, our POCs, things like that to give them a perspective. And he said they may come back and consolidate pieces. And that way, as a team, we're going to figure out how we collapse it. Okay. But we're going to tell them, hey, here's everything we would like. And let's work together to come up with a set of proposals for that. So just go into the proposal. You'll see the template, kind of use common language. So if you work on some scale out, work on a common language for that. Jay's going to post his piece as well. He's going to focus on scale up. So if you would like to do something that maps into scale out, but we're working system of systems is our theme, and around hardware software co-design. So take a look at the pieces, weave it into kind of the theme, but cover the pieces that you want, add it to that document. We'll all see it. And then by Monday noon, we'll pick Monday noon Pacific time at the latest. We would like people to start uploading into the Global Summit breakout session abstract in terms of that. But I'll start the prep with John Stewie and the OCP server team on Monday as well and say, here's what we have. And here's the additional work we're doing, which would allow us to kind of pull all that together. And you'll also see that we're referencing our framework is AstroSim, and our schema comes from the Keysight team.
Yeah, I'll be working on the convergence of the scale up and scale out. So I'll add on that. But the way I understood is that we'll have the common thing prepared, but we still register. We have to still register separately. Is that correct?
So it's just so everybody's on the same page. Everything will go into this common document, so you get to see it all. So
Okay.
contextually, you'll be able to write your section so that you look and say, "Oh, okay, I see how all these are connected." So you can fit into the theme, but you will grab your piece and create your own separate submission for your abstract, your social summary. What did we learn, and the title that you want for your presentation. Okay.
Got it. Thanks a lot. Thank you.
Yeah, because with that, we want to make sure that it looks like we actually work together as a group, I guess so that way you get to see it all.
Got it. Yeah. Thank you.
Oh, okay, thank you. Okay, and without further ado, Tushar, I will stop talking.
Jack, before we move off of this topic,
Sure.
Your guidance is great. We will have the spreadsheet ahead of time. Individual people will submit their abstracts, but so that later we can regroup them back into this work stream. It would be nice if people have a keyword such as AI hardware software co-design in the either the abstract or the portion that says what will the audience learn, have that keyword in there so that later when we put them together, because everything goes into Server, and Server is a big project nowadays.
Yeah, and so that's why we're discussing the theme with John Stewie. So I reached out to John Stewie and Rob Coyle just to make sure they understood the context of everything we're doing together. So to your point, Simek, but we're all using AI hardware software co-design and system of systems, because if you look at kind of the collective around the system of systems, compute is a system, fabric is a system, data is a system. We're using the schema to describe the system, and we're using the modeling framework to validate the system. So that's kind of the thread so we have both of those things that we're using as terms that will relate back to this working group of how we actually work together. And then one of the things that we're going to do is connect back with Tushar around ML Commons, traces, workloads, which hopefully we'll cover today because Yasha was having some questions. We start to convert some traces. And I see that Semantica and Matt on as well from the HPC side as we start to figure out, because what we want to do is really, as subsequent to Tushar's talk today, is figure out how do we actively go through, because starting Monday, we're all really kind of hitting the ground running. So if Tushar, as we go through, I'm going to kind of prep this, Tushar, if we can get a contact where we can start to ask questions about how we start to use the modeling, what kinds of things we can do, things like that, make sure that we stay connected. But if we have some things where we want to kind of push the envelope, and as Tushar, talked, there's Midlands at Harvard doing some work around the network simulation. AMD's been doing some pieces. HPE's been doing some pieces. So we're going to work collectively, not only to your point, collectively as a work group for OCP Global Summit, but also on the modeling. So this is really a cross industry collaboration and academic, in terms of this. So we want to make sure that, everybody, as we work together, everybody has kind of from an industry point of view, has their point of view and we contribute, but also based on the current state, and Tushar, I don't want to speak for you or for Yasha, but based on the current set of kind of academic industry, we want to make sure we highlight all of the academic contributions and leadership in terms of this working group, so that everybody, can see, hey, we're actually collaborating cross purpose, across teams, but also that, we're leveraging the academic community. So it does become a material example of something that we're doing. Okay. Can you still hear me?
Yeah, all good.
Oh, floor is yours, Tushar.
All right, awesome. Thank you so much, Jack, and thank you all for the invitation. Let me just I just want to double check my screen is visible, right?
Yes.
Okay, perfect. All right. So again, thank you, Jack. Thank you all. I think I know some of you, but for those of you who don't know me, I'm Tushar Krishna. I'm a faculty member at Georgia Tech. I'm a computer architect primarily by training. A lot of my group's work looks at new kinds of like accelerator architectures, NPU architectures, data flow optimizations, as well as fabric architectures for distributed ML. And a core, focus of my group is around developing simulation and modeling methodologies for, systems of systems, as the term that Jack mentioned. And so today my aim is to, present this AstaSim ecosystem, which we've been developing for several years now with, close collaboration with industry for advancing benchmarking and co-design for like these diverse AI platforms. So I'll start by just again acknowledging some of the folks who are involved in this. My students at Georgia Tech, Said from Meta, who actually developed the first version of this infrastructure. Then he was at HP, now he's at Meta. Taekyung and Srinivas at NVIDIA, Winston from Keysight, and his team who've been contributing several pieces. Of course, AMD, ML Commons, some companies from SRC, they're all kind of actively involved. So this is just a snapshot of folks I want to thank who are really, the ones who've at least contributed to the pieces I'll present today. So I'll start with the customary AI slide. Of course, AI is pervasive today. But this is more, I would say the algorithmic view of AI, right? Data sets and models. For those of us in this, virtual room, we're interested in the computer architect's view of AI, which is a lot of these platforms with, of course, NVIDIA on the top left, which is really dominating today. But there's, of course, several other platforms that exist from competing vendors like AMD, Intel, cloud vendor, hyperscalers like Google, Microsoft, Amazon, which have similar platforms, and of course, startups like Sambonova, Cerebras, and Grok. So I mean, this is of course the marketing view of these platforms. Like if we abstract it out, really most of them look something like this. It's not got all the pieces, but I think some of the pieces that I'm going to talk about. So of course, compute accelerators for AI or NPUs. These could be GPUs, TPUs, ASICs at the endpoints, and customized network fabrics to scale the task across multiple accelerators. And why do we have this? Again, all of this just setting context. I'm sure you're all very familiar with this. Large language models, large models which have like zettaflops of compute requirement, model footprints in tens of terabytes for inference, and also for training, and much more for training, which basically means that AI has become a distributed systems problem. GPT-4 was trained over 25,000 NVIDIA GPUs. Inference runs on hundreds of GPUs. So with this context, with the components of the AI platform in place, of course, data movement is a big challenge. And as I mentioned, like my work kind of focuses on modeling simulation, which I'll talk about today. We also look at accelerated architectures and fabric architectures. So with that, very quick context, let's dive in. So let me just set the context about, the problem space we are looking at. So coming back to this figure, there's diverse compute choices that are used in these platforms. And here is just a snapshot of companies that are using, a subset of these choices, of course, dominated by a lot of NPUs today, and GPUs, and of course, some startups also looking at compute in memory. A lot of networking choices. There's kind of the traditional electrical interconnects for scale up and scale out that NVIDIA, AMD, Intel are using. And there's also, of course, exotic technologies like photonics and wafer scale that some of these platforms use. Diverse memory systems, again, especially for this group, there's you understand like with things like CXL, there's a lot of options people are looking at with respect to data offload to near memory, far memory, and so on. And so this leads to a large cross-coupled design space where you have the architectural choices, the NPUs, the memories, the fabric. You have a lot of technology choices that are feeding in. All of this builds that AI platform. On this, now you deploy your software, which comprises of the models, software optimizations, which could include both lossy optimizations like quantization, sparsity, as well as like more lossless optimizations for like parallelism, scheduling, and so on. And if you're looking at LLMs, many use cases that basically boil down to varying sequence lengths. So this is an iterative process to, of course, get efficiency here. There's also a lot of co-design happening, as because this group is at the heart of it, which means that there's decisions from the architecture that affect kind of your software choices and vice versa. So there's a lot of design questions that people care about in this kind of a landscape. Somebody might be interested if they're coming from the model side about, platform requirements for agentic reasoning, say, right? Somebody might be interested in understanding the impact of parallelism on token generation. Closer to hardware, a memory vendor might be interested in understanding, well, what if I use some form of offload to say, far memory like CXL based or a CPU DRAM, what would be the impact? Like, would I still be able to meet my target throughput? Or if I'm an interconnect vendor, if I suddenly have this fancy photonic interconnect that doubles the bandwidth, how does it affect the end-to-end text summarization task, right? So a lot of questions here, which really motivated us to build a platform that helps us navigate these choices at a reasonable level of abstraction. So with that context about the problem, let me now introduce this AstraSim ecosystem. So to do that, first, what I'm going to do is I've abstracted this entire design space that I mentioned into some broad categories with these 7 colors here. So there's kind of the workload at the top, which includes the use case, the model, the optimizations. Then you have like the scheduling components, both for compute, like the compilation for that, and communication, the hardware architecture, which includes network, memory, and compute, and of course, technology choices that like in terms of new circuits and devices. And these are just some examples of, like problems people solve at different levels of this stack. Okay, so now what we do in AstraSim is we try to faithfully model this kind of a design space in this modular manner. And one thing AstraSim doesn't have today is kind of things on compute scheduling. So this is the one color that you'll see missing here, and not a lot of technology models, but that's why there's kind of these 5 other colors coming in here. And at from kind of a 100-foot view, AstraSim is really this piece here, this piece in the middle, which is looking at the workload and some of the system scheduling, and then it interacts with several external tools and frameworks via a bunch of APIs. So that's really kind of the architectural view of the framework. So AstraSim at a core is an entity that interacts with several tools and frameworks through these APIs. So what that means is and why do we do this? Because the aim is to allow the user to model the system that they are interested in the level of detail and simulation fidelity that they would like. And so this is all enabled by these APIs. And again, I'll go through some examples where this thing will be clearer. But the point being that what we have, so we have a GitHub, we have a website, we've done a few tutorials. Please do check these out. But what we have is really more like a reference implementation, and you can kind of customize it for your needs, as I said, through plugging in your own components via the APIs. So it's a vibrant open source community. As I said, we've been doing several tutorials, growing user base, and just as a snapshot of some of the folks that at least we closely interact with, who I know have been using AstraSim. And of course, very excited to work with the OCP working group on leveraging this. And as I mentioned, this is also something we're leveraging in the ML Commons Chakra working group that I'll also talk about in my talk today. All right. Any questions so far? This was all just setting the context, and now I'll go a little bit into the details of what the framework can do. All right, if no questions so far, let me continue. So really, let me talk about kind of the high level components in AstraSim, like its layers and APIs. So what I'm going to do first is just do a high-level overview of AstraSim. Then I'm actually going to go a little bit deeper into the execution traces, something around the collective communication modeling, and then towards the end talk a lot about extensions to AstraSim, which is where I would love to have a discussion in this forum and talk about some of the extensions that are already happening and some that we are planning. So with that context, at a high level, let me now walk through the different layers of AstraSim. So I'll start with the workload. The workload is really, it just means, the input, the model architecture, and all of the optimizations. So think of this as anything that you would say describe in PyTorch today, like in terms of a distributed workload. That is really what the workload layer is trying to capture here. And as an example, for training, the workload could be like the data set, the model architecture, and some of the system optimizations. For inference, we view the workload as the use case, which is again sequence length, the model architecture, model optimizations, as well as system optimizations. So this is the workload. Now, this is where the API comes in. So this entire workload is fed into the infrastructure via a graphical representation through this workload API. And this graphical representation is what we call as Chakra execution traces. So this is trying to capture the model, in a distributed manner. So the model, the parallelization strategy, the control and data dependencies, and the compute and communication order. So this is like a high-level snapshot of what the chakra execution traces are trying to represent. Again, as I mentioned, I'm going to do a bit of a deeper dive later in the talk, but at a high level, it's a graph of operators. So it's not, traces are not instruction traces or a memory address traces, but these are at the granularity of coarse operators. So, compute operators, could be things like matrix multiplications and so on. Like, so once you've taken kind of the model, sharded it across the GPUs, each of the compute operators is really, most of them are tensor operators that are running with the type, dimensions, and there's a notion of runtime that I'll come to in a bit. And communication operators, again, at the granularity of collective, so all reduce, right? That's the operator. So in some sense, this is just mentioning like per GPU what needs to run, right? And in what is the kind of dependence graph here. The dependence includes both data dependencies as well as control dependencies. And the goal is to kind of isolate compute communication operators and enable several use cases that, again, I'll talk about in a bit. So this is kind of the high level idea of the workload, right? Ultimately getting represented as this graph that's fed into the simulator. Now, this is where in the simulator, the workload layer comes in, and the workload rail is really just a parser for this chakra trace. So you have this trace that comes in, or this graph that comes in. You're basically going to parse it, understand all the dependencies, identify all the operators, and then feed them to what we call as the system layer in AstroSim. So the system layer has its own inputs that come via an API. And the system layer today is really a lot more optimized for communication scheduling. As I said, we don't have anything for compute. I'll talk about what we do for compute in a bit, but that's why the system API in AstroSim, specifies collective communication algorithms and scheduling policies. And the system layer itself basically now breaks down, takes the operators that came from the workload layer, and for the communication operators, it breaks them down into finer grained sends and receives based on the collective algorithm. So again, things I'll talk about in a bit, but fundamentally what it's trying to do is I have an all reduce, I have a collective algorithm that I've specified, maybe a ring all reduce or a double binary tree. It's going to break it down into individual sends and receives and send them down via the network API to a network simulator. Similarly, it's going to take the compute operators. Today, we don't have like a detailed compiler. So it basically takes the compute operator and sends it via compute API to a compute simulator and so on. So the compute simulator's job is really to now take this operator and simulate the performance. And again, depending on the degree of fidelity, you might plug in different compute simulators. So what is the role of the compute simulator? I have this compute operator that I got from the chakra trace. I simulate the performance and get a certain time. And how do I simulate the performance? That's where you can plug in compute models of varying degrees of fidelity. You might we provide like a roofline model that's obviously the fastest, but in terms of accuracy, not the most accurate. We also provide the simulator called ScaleSim. This is a different effort from my group where we had developed like a TPU systolic array based accelerator model. So slightly more cycle accurate, and but slower. There are some efforts. I know HP did some work where they actually took this. They can actually deploy the compute on like a real GPU and get the compute time back. But again, you can plug in different compute simulators here. So that's the idea of the compute layer. Similarly, the network layer. This is, I would say, the most robust part of the infrastructure, given that a lot of AstroSim kind of started off with us looking more at networking. So we have this API which has these sim sends and receives, scheduling kind of callbacks, and so on. And the goal of the network API is to interact with a network simulator at the backend. So the network simulator is where you would plug in different network simulators, open source, proprietary, and simulate the network behavior that you care about. So this is actually where we have several simulators that we already support. So we have a couple of analytical models in the infrastructure that we've created. One which is kind of congestion unaware, one which is slightly congestion aware but simpler. We used to have Garnet from Gem 5. It's deprecated right now. HTSim is actually something that Marvell contributed on, like just 2 weeks ago. They pushed it into the infrastructure. And NS3 is a simulator we've been supporting for a while. So all of these, again, are plug and play. You just, as long as you have the API, implemented, you can run these. And we're also doing some work where we want to take the network traffic coming from AstraSim and run it on a real network, right? So basically, you don't need the GPUs anymore, but you can simulate actual real network traffic. So this is also something we've been trying to do. So again, same idea. As you go down, fidelity increases, simulation speed decreases. Again, additional proprietary network simulators are also being used by several of our collaborators.
Tushar, question.
Go ahead. Yeah.
So HTSIM, what exactly you're using it for in AstroSim?
So good question. So so far we haven't used, I mean, when I say we, like at least we've not used it so far. This is something that Marvell contributed. My sense is that since, and I guess folks here actually might have more of an idea. My high level sense is that HTSIM is of course the simulator that is being used by the UEC consortium, and there's other companies that are using it for various reasons. And the idea of plugging it into AstraSim is so that you can get like more realistic AI traffic kind of being fed into the simulator, right? So that's what I would say. But this is one that, as I said, was contributed externally. We haven't tested it out in my group, at least. What we've used so far in my group has been more the analytical models as well as NS3. But
Right. So I mean, HTSIM is basically a simulation model for the fabrics.
yes.
And essentially, we are trying to get idea about congestion control on a
Yes.
fabric. So you're
Yes.
right. And it's very modeled on the AI traffic, not so much on the HPC traffic.
Yeah.
And that's where my question was. I thought the AstroSim is mainly focused on the HPC. Is that not true? Or maybe I might have a wrong.
Oh, no, so AstraSim is mainly focused on AI.
Oh, it's mainly focused on it. Okay.
Yeah.
Got it. ML Commons is on HPC.
ML Commons is AI, like a machine learning common. Like it is explicitly AI. So we are trying to extend it to HPC, and I'll talk a little bit about that. But it is primarily AI. So yeah.
Okay. Then I think then it kind of fits the model. Then
yes.
Yeah. Okay,
Exactly. So that's the intent. So I think the intent is to study congestion control for AI traffic, especially for the scale out part, where I mean, scale up, people have more customized collectives, topology aware collectives. Scale out is where you start seeing a lot more congestion. So again, HTSIM NS3, at least in my mind, play a similar role where they have much better models for congestion control. I know Alibaba uses NS3 for some of their explorations. And same thing and same idea, right? Like, I mean, there's no different simulators, different trade-offs, but the idea is really view AstraSim as a glorified traffic generator into a network simulator. And the traffic is the AI traffic. How do you get that? You have the AI workload, distributed AI workload coming in from here. AstraSim is going to take the workload, break it down, implement the collective algorithm analogous to, say, an NVIDIA Nickel, break it down into individual messages, sends and receives, and then call a network simulator to simulate it, right? So that's kind of the high-level picture.
Got it. Another question, a little bit naive.
Yeah.
So the endpoint, which is doing any kind of a credit allocation or running a CC algorithm, sender or receiver based, which boundary is gonna be?
That's going to be all inside the network. So that's all going to be part of the network simulator, right? Like, so the network simulator's job is to do all of that, if that's what you meant.
Yeah, I mean, it's going to sit on the NIC side and physical boundary and the physical topology, but it needs to still interface with the collectives, right? Libverbs or whatever stack we have on the top.
So all of that is good question. So all of that is so. Let me answer it in two ways. So the role of the system layer here is to implement the collective implement the collective library and kind of break it down into the collective algorithm, which really just boils down to send and receive messages. Now, once you have a send and receive, if I'm doing something like RDMA, yes, that needs to interact with an IB verbs to create the actual queues and so on. That is technically code that will sit here from at least our perspective. I mean, like we've kind of we've kind of given you the messages that you need to send and sent it down to the network simulator, and the network simulator is going to translate it to whatever underlying, kind of transport you're going to use, right? That's kind of the way we've done the separation of concerns here. Yeah.
Got it. Got it. No, that makes sense. And thanks for explaining it.
Yeah.
Appreciate it. Thanks.
So
I have a question.
Go
Just
ahead.
a quick one. So can, for example, we plug in a network simulator using NS3, for example, network simulator? We can do that, right? So I can build my own simulator using NS3 and I plug it in here.
Yes, exactly. That is the whole idea. Yeah.
Thank
In
you.
fact, we have a page on how you plug in, and that's kind of how we did all of these. And the idea is that, so at a very high level, the idea is that, so we've actually tried to do it in a way that the network simulator stays kind of standalone. We did not want to build something where everything is plugged into this one big monolith piece and just things become very hard to manage. So you have your own simulator that exists. All you do is you basically have to include a header file for the API. You add some glue code to the AstraSim side. So in the AstraSim, there's some glue code that sits for each network backend simulator, which is more AstraSim specific. But your simulator stays kind of, it's kind of a sub-module that comes in, which stays behind, which means that it can be even, right, hidden proprietary, whatever, right? And that's the way. In fact, AMD has been doing that quite a lot, where they have their own network simulator for their GPU networking, but they leverage the front end. They've actually been adding some glue code to the system layer to make things a little bit more accurate and cleaner, which I'll talk about towards the end. But the whole vision is that everything stays here, and all AstraSim has is some glue code to interact, but really the interaction is via the API. Yeah, that's what you do. And any other question on this line before I move on? Yeah.
Hey, Tushar, one more question.
Yep.
Yeah,
hi, Vipin. Yeah.
Where is the optimization model here in this system?
So can you elaborate? What do you mean by optimization?
Oh, for example, if you have like data and communication overlapping or those type of optimization.
Yeah. Makes sense. So let me come to that. Actually, in a couple of slides, I'll give an high level example, and then I'll come back to where the thing. So this is kind of an example of just different kinds of topologies we model. But again, I'll say that when I say we, this is the network simulator, right? So if a network simulator can model like different topologies depending on its capability and model its own, routing, flow control, and so on based on its capability. But at least the analytical model we have right now that we've provided, models a lot of these, like hierarchical tiered topologies, as well as a few more custom ones. And just to complete the picture, there is also what we call as a remote memory layer. This is very naive. Like we had actually, implemented this for a project we were doing to understand CXL based offload, but it's a very naive implementation. We have the API, but there's really just a very simple analytical model. Just 2 tiers, like local memory, you get this bandwidth, and latency, remote memory, you get that, right? That's it. So again, this is kind of a place where, especially for folks interested more in advanced memory systems, there is an opportunity to add more detailed models to do some of those studies. So with that, now let me actually show like a very high level example, and as part of it, maybe try to answer Wei Feng's question. So suppose my aim is the following. I want to simulate a system with a new network fabric, but the same GPU. That's my goal. I collect a trace. Let's say I collect this from a real system. And again, I'll describe how we collect traces and all in a second. So I collect this, trace. It has the compute and in communication times. It has the dependence. For the compute, I decide to just replay it through the simulator. I'll just extract the runtime. For communication, I decide to actually simulate it. So it's an all reduce. So I use AstraSim, simulate the all reduce algorithm, schedule it, get the exact send and receive messages using the network API, call a simulator of, again, whatever degree of fidelity. And finally, it says 20 microseconds for this. And now what AstraSim understands is the dependence, right? It understands the dependence between the compute and communication operations, how much of it can be overlapped, and says that, this is the amount of communication that's exposed. So that's the way you would use it. So now coming to, in fact, where an optimization engine might sit, actually, it will sit somewhere here. We don't do that optimization in AstraSim, like in the sense that we we do the scheduling based on the dependence graph that Chakra gives us. And right now we do a very greedy scheduling where, if there's two operators that can be scheduled concurrently, I mean, literally like whichever one has the lower ID gets scheduled. But here is where two levels, right? So first, there is a global level of optimization, like scheduling you could do, where you could potentially play around with the scheduling of these coarse operators of what communication gets scheduled first and so on. There's also another level of optimization one could do, which is where once I break the communication down to like smaller sends and receives, and potentially break the compute down further into finer grain operators, you could do some form of scheduling here for better overlaps. I mean, you're going to get the compute and communication times from here, but ultimately the goal is get all of these times. Now what you have is this big graph where all the times are kind of embedded, and you're trying to see, what is the best schedule for getting the least time, right? So these are things one can add. Like, again, that doesn't necessarily exist. So we just do a simple scheduling for now. Does that answer it, Be fair? Yeah.
Yeah, thank you.
Yeah.
Hey,
Are
sir,
the schedules pluggable, or we can add the schedules? Because you and I've talked about everything
Yeah.
from chip
So
design to system design, which I would use different schedulers, so I could do that.
yes. So again, as you said, right, I think there's scheduling happening at various, granularities. I would say there is kind of a more global level of scheduling, which is simply, I have the Chakra nodes, the compute communication operators, and just identifying, if there's dependencies, can I schedule both these compute simultaneously, communication simultaneously? But now it depends on the available resources. Like I might want to schedule, two compute operations simultaneously, but my GPU doesn't have enough SMs to do that or whatever, right? So that gets to like the second level that really depends on the available resources and how you want to overlap certain things. That is a piece that can be plugged in. In fact, that's one, I would say, contribution that's coming from AMD soon. Like they are actually adding another layer here for being able to do finer grain scheduling. Like what exists today in AstroSim, I would really say is more coarser grain scheduling. Yeah. So, but that's something we would like to do, so that yes, schedules are also something you can potentially plug in as options.
Okay, because with that, then I could do the data services you and I discussed. I could now map that the compute. It's a compute communication, but it's a different layer in terms of the scheduler.
Yes. So
Okay.
that would, I think, again, so I think these are great questions. I think these are some of the pieces that don't really exist, but like there's mechanisms to kind of support them, and yeah, and we would love to kind of would love to help enable that. Yeah. Okay, so just to summarize the AstroSim part of, at a very high level, the key features, we want to model this co-design stack. We have these workload system network memory compute layers today with, plug and play support via APIs, support arbitrary workload parallelization strategies from the workload side, model system level behavior, and of course, run network and compute simulations. So with that,
sorry, I had a question on that, and again, a little bit of lack of my understanding. So, the parallelization or the optimization also can be network aware in the sense
yes.
that
No,
part
I
aware,
see
like
where
we
you're
have,
coming. Yeah. No,
right?
that's a great question.
And that I don't. So, I mean, if let's say I have to provide that information, how would I do that?
Yes, so I'm actually going to now do another forward pointer to the stuff that Keysight is doing with respect to a system scheme. So let me first kind of reiterate the question just so that we're all on the same page. Right? I think Jeff's question is coming from the fact that this is great, you have all these abstractions, but it almost then seems like every layer is making decisions independently, which is a bit challenging given that there are decisions that need to be taken across the stack. For example, the workload parallelization heavily depends on your actual network topology. For example, you might want to do tensor parallel within the scale up domain and data parallel scale out. In fact, even between the system layer and the network layer, the collective algorithm you choose depends on your physical topology, because you want to have something that's topology aware. So you do need some global way of, understanding the pieces. So because of this modularity, what we've done is, yes, you have these individual files coming in. And today, I think it's a little bit more ad hoc. Like as a user, if you are using the entire framework, you know what the topology is, you know what the system is, and you kind of make those decisions. but there is no clean way today of just probing a unified, let's say, database to kind of get a sense of the system and make, these decisions automatically. And that's where, so Keysight has actually developed this, infra.proto infrastructure where you can describe this, and at least the way, and again, Winston is on the call, he can chime in, but the way I understand they use AstroSim or their own simulators is that, you can probe that from anywhere, which essentially then lets us do exactly what Jay you asked. So that's, I think, one of the key pieces we would like to bring into this to allow this co-optimization to happen automatically. As I said, today it's more, I guess, user defined because the user knows exactly what is happening at each level.
Right. And who's the person from Keysight? May I
Yeah,
know?
so Winston is on the call, and we will actually, this is the piece that I think in the very beginning, Jack was mentioning that we're trying to, come up with this standardization of, the system schema infra.proto. And so I think, yeah, Winston, I don't know if you wanted to just chime in on
Yeah.
that for a second. Yeah.
Yeah, I mean, I think the key there is like we need a common language, right, in order for the various layers of optimizations or scheduling to be able to leverage the same information and optimize across the stack.
Yeah, so that's
Got
basically.
it. Yeah, thanks for Winston. Thanks, Tushar. I won't disrupt more.
Yeah, no, so but
some...
I think so I think in terms of the engineering, our vision is still the same. We would still like this modularity. Each of them has their own input file. So I think the way we are envisioning is, there is this common system that gets defined. Each of the individual entities probe that and populate their own individual files. You might still have your own proprietary network simulator. So again, the idea is not to have just everything, but you kind of probe like a common, in database to get that populated and then do these, cross stack optimizations, right? Yeah.
So
Thanks.
Tushar, Prakash has a question, and we have 15 minutes left. So kind
Okay,
of gauge
got it.
accordingly.
I'll
So,
keep aware of my time, and let me just take a look at the question.
Quick
Prakash,
question. The similarly, like a network simulator, I have a question on the compute simulator part. Is there any mechanism to simulate the core, whether it's the RISC-V or RISC or ARM or whatever?
So again, so good question, Prakash, right? So in principle, yes. So again, I'll say that in principle, the idea is that you call, this through a compute API and you run whatever simulator. We have not tested any of these other simulators yet. So this is actually, again, one where we do have this active effort with IMEC. So they're actually trying to do exactly what you mentioned. I mean, today what we do is we take this coarse compute operator, call a simulator, and that simulator should just give you the time, right? So you could just call, like, take a matmal operator, call a RISC-V simulator, and it, gives you whatever runtime. But what that's missing is, there might have been some, additional compiler passes earlier. So again, that's, I would say, the mechanism that's missing. So I can envision that there's a bit of a software stack sitting here for breaking the compute operator also into finer grain tiles and then calling your simulator. Or like today, what we do is you just take this big operator, which is like this tensor matmal that needs to run, call the simulator, and its job is to simulate it, right, and give you the time. So ultimately, again, my point being, yes, you could simulate RISC-V cores. That just really, again, hidden here. All we care about is give me a time, right? How long did this matmal take? And so as long as I know how much time this matmal took, and as long as I know how much time this all reduce took, because I have the dependence, I can kind of try to see how much of it I can hide, right?
Definitely, we'd like to. We'll take it offline, and I'd like to get involved in that. We are the RISC-V company, so we can help on that part, and then take advantage of the other parts which you have. So.
Yes, perfect. Yeah. Thank you. So let me just see. There's a question on the chat from Victor about, I'm just going to read it out. So Julia focuses on full stack. Victor, did you want to, maybe Victor, actually, let me very quickly talk about Chakra as well. And then I think your question might be more, I think it might be the right time to talk about it. Does that make sense? Yeah.
Yeah.
All right. So let me, in next few minutes, very quickly talk about the Chakra execution traces, right? So as I mentioned, like this is the way the workload is being fed into the infrastructure. And what are these Chakra execution traces? So from a cartoon level, what we're trying to do is the following, where I have, say, a DNN model here. I have a cluster of these NPUs. Let's say I decide to, run this over here in a data parallel manner. Let's say, so basically forward pass for all these operators. Then I have a backward pass where I have weight and input gradient computations. And I have these red circles, which are, say, representing an all reduce, right? So this is kind of an abstract view of what the trace will be that each of the NPUs is running. And this is part of this, broader effort that we are doing with ML Commons. I co-chair the Chakra working group with Srinivas from NVIDIA. So we started this effort about 2 years ago. The goal is to kind of build consensus on the the trace format, the tracing methodology from frameworks like PyTorch, and kind of provide some downstream tools for analyzing the traces and running the traces, and eventually create a benchmark suite of traces that we are planning to release to the community. So that's kind of the broad goals. And this kind of figure captures these goals in a more visual manner, where the idea is that, like a company, say like a Meta or a Google, is collecting these traces in production in a proprietary manner. But these traces now come into kind of the open community, where we have like the Chakra infrastructure for maybe trace analysis and visualization, so on and so forth. And then you can take these traces and do two things: either replay them on a current system or simulate them. So I'll very briefly talk about all these use cases in the next couple of minutes. So first, let me just talk about trace collection. Trace collection is really, this is the schema like that exists today and this is from our Chakra's GitHub, where these are I mentioned, like you have the compute and communication nodes, and these are all the types and so on, and they're the metadata. And the idea is that these traces can come from various levels of the compilation stack. So you can, of course, you start with the pre-compiled, original model. You can now have a distributed version of it, which is, both, like you kind of have a distributed version, which is either platform agnostic, or you might have some platform dependent transformations also coming in through the compilation flow. So an example of this would be something like PyTorch FX graphs, like that's the granularity. Or you can now take and run this on the real system and collect traces from the real system. So this is what exists today. This is when we started the working group, we kind of started with this, and this is what we support today, where you can actually take, PyTorch code, like you can take a model, distribute it via PyTorch, run it, and you can enable these hooks in PyTorch to collect these execution traces. This is thanks to a lot of effort from Meta. And we also have efforts where you can synthesize these traces synthetically. You could use analytical models, statistical models, and so on. So basically, this is an ecosystem of threads we are pursuing in the working group to just come up with a suite of traces, either from real systems or synthesize them. And as I mentioned, this is just a snapshot of what these traces look like. This is a pipeline parallel trace. This is a slightly more sophisticated trace. Very quickly walk through, the components. So you can take the trace, you can either replay it on a real system. So Meta, NVIDIA, I know some of these companies have been using these traces for that use case, so that they can tune, actually related to the question earlier about optimization, right? So the use case of the trace is I want to understand the right communication knob, see how much I can overlap, but I don't want to rerun the entire model over and over again. So I just take the trace, replay it, like maybe just replay the communication so that I can, do some of the optimizations on the software stack for my current system. Or you can take the trace and simulate it on an infrastructure like AstraSim. So AstraSim is, again, just, I guess, one of the simulators that we view that can consume these traces. But again, other simulators exist. For example, we have a lot of working group members. Again, Winston is the person I'm referring to every time. Like, Keysight would say take these traces and run them on their own simulators, right? And similarly, the other companies that are actively using these traces. But AstraSim kind of has kind of a reference, Chakra feeder that within the workload layer to run these traces. And finally, as I mentioned, there's some supporting tools for visualization and so on. So let me pause here to see if there's any questions on Chakra, and maybe this is the right time to also see if there was questions on the chat. I think this was specifically about how we could leverage Julia. So I'll have to maybe
actually,
discuss that a little bit
probably don't have
offline.
to expand here because I've been joining the chapter meeting for almost a year now. So I was going to ask the meeting there. The reason I bring it up here, I believe is something that cannot be done. It has to be done together with both something change on the hardware side, as well as, because I know chapter is based on the torch profiler.
Yep.
That probably need to have change as well to be able to have more kind of a like time-based, elapsed time-based matrix.
Got it. I see. Yeah. Fair enough. Yeah. I think so. Again, the way I view it from an abstraction level is our aim is to say that, this is the workload trace and this is its format. The way you get it is, I mean, today we seem to have a lot of support in PyTorch, again, just because of, its use, but I don't think we're kind of limited to that being the only mechanism of getting traces. So the idea really was that part is agnostic, and we would love to have other front ends that can generate traces. I think that's the way I would view it. And as long as what you generate has this, I mean, it follows kind of the schema in terms of, the nodes and the types and so on. We call that as a chakra trace, which basically means as long as you can do that, the downstream tools would just work. That's kind of the vision. Yeah.
Yeah, I'm not sure anyone else have a question. Please interrupt if you have. Just follow up on the same thing. So this group is about software hardware co-design, the composable hardware. The I think the challenge is how to real time make decision that something is running slow and why. So I know that the current trace is very heavy. So how do you get that real time is the question.
That's a good point. I don't know if I understand. So I think is part of your question just the fact that the trace itself is like static, or is that your worry, or is?
Yeah, it's a very too. I think overhead is high, so so you running in production create very heavy workload. So you need sort of kind of aggregation instead of keeping all the details.
Yeah. No, that's fair. So
yeah.
that's a great point. I think that's another thing we've been trying to do where, I mean, in fact, some of the synthetic trace generation methods are trying to do that, where in principle, you don't need to kind of take this massive trace where there's obviously going to be a lot of replication of, operators as well. I think that's an interesting researchy question on how do you compress it? How do you maybe describe it in a way that you don't have to have the entire graph being fed in, but maybe either some other version of it, or you can kind of create the graph as you go. I think those are all, those are all
the reason I'm bringing it up is I worked for Oracle for 17 years. Oracle, there is this kind of a so-called AWR, automatic workload repository. They do kind of aggregation on the fly. That's why
I see. That would be great to chat about. And as you said, since you also participate in the Chakra working group, we'd love to have maybe a presentation from you about some of that. I think that would be.
Yeah, I was trying to ask this question there. Just yeah.
Yeah. So if please do send me an offline email, and would love to schedule like a discussion that you can lead around this. We've had some of these discussions, and I don't think we've kind of had very fuzzy ideas, but I think this is the first time I'm hearing a very concrete suggestion, as you said, Oracle, we've done something like this, which would be really, really valuable.
Yeah, it's a single instance. It's not distributed though. That's the problem.
But at least it's a start. Yeah, awesome. Thank you. So in the interest of time, let me try to go towards
when you say chakra was timing, do you mean time synchronization?
Oh, sorry, no. So by timing, I just meant that how much time did each operator take on the real system? So this is kind of like I ran this trace, I collected it, and how much time did this compute operator take? How much time did the all reduce take? All of that gets embedded into the graph. And the tools can either choose to use it or ignore it, right? For example, I mentioned that use case where in AstroSim, what we typically do is we just, because in fact we don't have a detailed compute model, we just reuse the time from the trace for the compute, but communication is where we do the simulation and like try all of the other things, right? That's the idea.
Thank you.
All right, so let me jump a little bit ahead. I had something about, so there's a lot of things around collective modeling that exist in AstroSim, and I think one slide
Can you also share the slides when you're done?
Yes,
send me
I will.
Send it to me and I'll post it.
Yeah,
Thanks.
perfect. Yeah. I'll just take one slide to kind of mention that in AstroSim, again, kind of with this whole API vision, this is something we did like just last year. We added like a collective API where you can feed in your own collective algorithm externally. You could describe it in MSQL Lang. You could have a collective synthesizer. You might have your own custom DSL. So that, I mean, our aim broadly in AstraSim has always been that let's not try to implement too much inside this, because then it gets into, validation issues and maintenance. Let's try to leverage external frameworks that are already doing this very actively and maintaining things, and just provide a way of, composing them. That's kind of, just wanted to mention that with collectives, we are doing that. So collective API also just uses the same Chakra format for actually related to the optimization piece that, Weifeng, you asked. Our vision is that everything becomes like this Chakra graph now, where compute communication is all these finer grain operators in the system layer, so that then you can start doing optimizations. So we've not done the optimizations, but we're kind of, the representation exists. So let me now take the last minute to just talk about some of the extensions, which we can of course talk about in future meetings as well. Some of the which I already mentioned. So HTSIM recently came, thanks to Marvell. I mentioned this scheduling layer that AMD is adding to do more finer grain things, to understand, at least from AMD's perspective, things like thread blocks and so on. So it's, I would say, more of a scheduling model for their GPUs. This whole infra.prodo database that Keysight is adding, that the entire infrastructure could use. I mentioned the compute API efforts. At least, there is one active effort I know of with IMEC. One of my students is interning, so they plan to kind of get this released as well. And there's also this very cool thing that, Keysight developed, where they have the ability to run AstraSim on a server and have like a client probe it, which is also a very, very valuable piece that we've, Keysight is looking into, to contributing to the open source. And the second piece, which relates to, I think, this group here in discussions, like with, with some of the members here, like Jack, Samantika. So, we've talked about having SST as another network backend, which, some companies are interested in. There is some work as part of these SRC centers I'm part of, where we're looking at adding a photonic fabric plus technology model. So some efforts there. Jack is, of course, very excited to add like a potential storage API, like add storage models. Related effort in ML Common side, Oana, who heads the ML Common storage working group, she's looking at like extending the Chakra schema to also include storage. Today, it does not include that. Yeah, so I think that's basically, I'll stop. Really, my last slide about some of the things.
Tushar, so this is Jack, and you owe me an introduction
to Anna. Yes, I will do that. I know. So
okay.
This is this connection needs to be made. She's traveling right now. So I just decided to wait till she's back and do that. But yeah, no, thank you for the reminder.
Okay, so as we close here, I know we're going to have a lot of questions. So number one, how would you like to handle questions, follow-ups, details, things like that as we kind of go through? So that's the first part. And the second part is we talk about infra.proto. We've exchanged email with the OCP, Open System for AI, and they agreed to support us standardizing the schema through OCP. And so I'm hoping that Winston and Kingshuk will kind of help us take the lead as we write out that specification for the schema that will be supported by OCP around their infra.proto.
Perfect. Yeah. So I think to just answer your question, so two things. So one is, I think from a pure usability of AstraSim, we have the website, we have a mailing list. So if anybody wants to try it out, please, I would say, take a look at our tutorials, which I think are very comprehensive with like examples. So at least that'll get people who've not used it started. Then the mailing list is what we use for answering questions and kind of collectively, either my students or like our colleagues do answer. I think there are additional questions around extensions of the tool and things like that, which is where I guess like a forum like this would be interesting to discuss. And I think part of what Jack and I talked about has been that, if we can, kind of think a little bit about a wish list of features we would like to get here, especially from, the interest of the different OCP working group members. And as we kind of get closer to the summit as well, we can then start thinking about, how these come in. But I will again add that it is an open source project. So, please feel free to contribute, add PRs and like, contribute. I mean, that would be one way to get, a lot of these pieces into the common infrastructure. Yeah.
Yeah. So I know Prakash has a question. And Prakash, one of the things that Tushar and I talked about is, from a compute and a network point of view, could we simulate even chip designs and things like that in terms of some pieces around mesh, around cores, around a number of things. So we can take that one offline, Prakash. So go ahead, Prakash, ask your question.
Yeah, quick question on the Chakra part. Is it also dealing the automotives or it's only for AI ML?
Oh, so
Means
that's a great
automotive also has the
question.
AIML part though.
So it is. So I would say that it is AIML from the perspective that we have support in PyTorch to collect traces. Maybe that's the way I would say it's AIML. But and the traces themselves in terms of the operators are the operator types. I mean, we have a notion that it's AIML because of which we are like, oh, this is compute, and it has these types, and communication has these types. So in principle, a trace is a trace. I mean, you could collect it for any workload, but in that sense, it's a little bit tied to AIML. And I think that has what has helped us to kind of get these traces at a very coarse granularity, because we know things are static. I mean, for the most part, ML, the workload graph is static. There's not much. It's not going to be very date input dependent. Let's ignore sparsity for now. But that's why. And there's some, again, offline discussion about how MOEs kind of come into that mix, but ultimately that's why it's we can do this. It's very coarse traces. And the whole vision is that you can take an operator and then break it down further into whatever granularity you want using your tool chain, right? Like that's the idea.
Seems like framework seems to be pretty common. It can be used for many applications.
Yes, exactly. Yeah.
Okay,
But
we
we
are
cannot
open
write it for anything else. That's what
we are open, and then boundaries are very blurry. Like we can't say that automotive does not have AIML. They have the AIML too. So yeah.
Cool. So we've hit the more than the top of the hour, Tushar. We really appreciate you attending and giving us an overview here. And as we work on our sprint towards the global summit and the modeling and the pieces, especially as we standardize on the schema, we are going to be collaborating with you more, and we very much appreciate on you joining the group and helping us out.
Perfect. No, thank you so much, Jack, and thank you all for all your questions and engagement. So I'll share the slides with Jack, and he can share it with everybody.
Yeah,
And
they'll go.
Do you have a Slack or Discord?
Good question. So yeah, we actually do have a Slack for AstraSim that we'd created. It's just something we've not been using very actively. I would say at this point, Hisham, the mailing list is really what we've been using for most of the kind of.
Good. Can you just put a link to the mailing list, please?
Yes, I will. So that's on the, So as soon as you go to the AstraSim website, like actually on the AstraSim GitHub, the mailing list is there.
Okay, good. Thank you.
All right.
Okay. Good. Okay, we'll catch up, and
Jack, the link to the spreadsheet that you said you're collecting all of the abstracts for Global Summit.
It's in our share drive, and I will send it to you personally right after this meeting, so you get a link to it and you can see it.
Thank you very much.
Sure. Anybody else have any questions, things like that? But the recording will go up, and the slides will be posted to our presentation directory as soon as I get the recording. Thank you.
All right. Thank you all. Take care.
Thank you, Tushar. Thank you.
Thank you.